Morning, everyone. Whether I'm audible? Yes.
Yeah, sir. Good morning. Good morning, Srinath, sir. So you're audible.
Yes. Ma'am,
Yeah, sir.
actually, I have
Also, I've
connected.
given you the sharing rights, sir.
Yeah, I have connected in two systems because you're having one standalone system, making use of that.
Okay. Okay.
So can you please give the access for that also?
Yeah. Okay, sir. I have. So, like, to which system should I give you the presenter rights? Because at a time, only one system can have the presenter rights. So, in one system, I have
Yes, yes.
made you the
I can. Yeah,
co-host.
yeah. I have. Yes, yes. One system you gave me co-host.
Yeah,
Another
and the
system you
others,
make me host. Because
and the
one of the software, one of the software is installed in the system what I'm talking, and the other one
okay.
is present in the one which I am
Yeah.
the standalone one.
Yeah,
Yes.
yeah. Okay. So since you have the co-host role, so even you can like
I can.
change the presenter rights anytime. So whenever you feel
Okay.
comfortable.
Okay
Yeah,
then. Okay. Okay.
yeah.
Fine.
Okay.
Thank you.
And so we'll wait for another 5 minutes. So as all the
Okay.
participants have not joined yet, and then we'll start.
Sure then. Fine. Fine.
Okay. Thank you, sir.
Hello, ma'am. Hello.
Yes, sir. Yes, sir.
Yes.
Yeah.
Can you make? I have one more login. Can you make that as a host?
One
Uh,
more login.
I have
Sir.
in the name in my same name. Can you make
Sir.
it as a host? Because I tried sharing it.
No, sir, no, sir. We are
That's why.
getting only two systems. Like other system, we are not getting with your name. So, did you use any other name?
No, same name. Same
No,
name.
so with this name, we are having only two systems connected, and there one
Fine.
system I have given the presenter rights, and the other system as the co-host.
Okay.
So we are
So
not
because
able
I
to
tried
find.
sharing, I tried sharing it, but it is not sharing in the co-host system.
So in the co-host, like, should I give the presenter rights?
Yeah, I need both the systems presenter rights.
So at a time, only one system can have the presenter right. So,
Okay.
the system in which you have the co-host role. So one thing I'm doing in both the system, I've made you the co-host. So you can easily like change the presenter rights, switch the give like just you have to right click and you can change the
Okay.
presenter rights, change role to
Make
make
presenter.
presenter.
Okay.
Yeah,
Okay.
yeah,
Fine.
that can
Fine.
be
Fine.
done.
That is
Yeah,
good. Yeah. Fine.
yeah.
Thank you.
Okay, okay. Thank you, sir. Good morning. Good morning, Srinath sir. Good morning, Abhinandan sir. And good morning, all the participants. Today is the 9th day of this program. So I welcome you all. And for today's session, we have with us Dr. Srinath sir. He'll be taking the session. So before I hand over the session to Srinath sir, I would like to request Abhinandan sir, like sir, if you have any announcement to make for the Open Pass Submit, then you may do, sir.
Yeah, ma'am. Today is a reminder. So
Yeah.
the session would actually start. It is scheduled today from 9 morning US time, CDT time. So the link that I have shared earlier in the class, please do join. So once again, I will uh, I will actually share the link on the chat window. So.
And that slide is also uploaded on the Drive folder. If any one of you are interested, you
Yes.
can check. You will find the link over there as well.
So please do register and attend. There are very interesting talks. And today I am also going to present our experiences with uh, with this FDP also. So please don't miss. Okay. So yeah, thank you, ma'am. So let's, hi Srinath, yeah, please continue the
Yes.
session.
Yeah.
Thank you.
Good
very
morning.
much.
Yeah.
Thank
Good
you.
morning, all of you. Yeah.
Yeah.
Shall I carry
So,
over the session?
so I'll just give a brief introduction of you,
Okay.
then
Okay.
we may start. Sir.
Okay. Fine.
So good morning. First of all, thank you, Abhinandan sir. The link has been shared in the chat box as well. And today's session will be taken by Dr. B. Srinath. So he received the Bachelor of Engineering degree in Electrical and Electronics Engineering from the Annamalai University, India, and the Master of Engineering degree in VLSI Design from the Karunya University, India. He also received his PhD from School of Engineering and from the School of Electrical and Electronics Engineering and SRM Institute of Science and Technology, India. Now he's working as assistant professor in the Department of Electronics and Communication Engineering, SRM Institute of Science and Technology. His current research includes low power physical design and testing of VLSI ICs. So with this short introduction of Srinath sir, I request Dr. Srinath sir to kindly start with the session.
Thank you, ma'am. Thank you for the, thank you, ma'am. Thank you for the introduction. So let me share the screen first. Yeah. So hope my screen is visible to all of you. Yes. Is it visible? Abhinandan?
Yes, so it will come in few seconds, I guess. It's showing up. Yeah, okay.
It is showing us only viewing Srinath's
Yeah.
application.
Yeah,
Let us wait for a minute.
It is right? It is visible.
No. It is still working on that. So viewing Srinath application. Is it an Ubuntu, Srinath?
No, it is Windows. The same one.
It is showing us it's starting to share content which not yet like came up, but it will come, I guess. So can you just close this sharing once and start sharing once again?
Yeah. Is my screen is visible now?
No, sir, not yet. It is taking time.
Yet.
Okay. Just a minute.
Srinath sir, are you sharing any particular application or you're sharing the whole
No.
screen?
I'm sharing it. Just a minute. I'm sharing.
Now the screen has been shared, sir.
You are able to see the screen?
Yeah,
Yes,
I'm
sir.
we are
opening
Yes,
it.
sir. Yeah.
Okay, just a minute. Yeah. Are you able to see the screen, ma'am?
Yes, sir. Yes, sir.
The presentation screen, are you able to see?
Yeah. Yeah. It's OpenLN tool
Thank
and
you. Thank you.
installation.
Thank you very much. Thank you, ma'am.
Thank you, sir.
Yeah. So good morning, all of you. I'm going to present today about the OpenLane installation. First, I will give an introduction about OpenLane tool, and then I'll tell you about how to install the OpenLane tool, and then we will see some small experiments on how we can make use of OpenLane for generating the GDS, okay, GDS2 files. So first thing is that yes, OpenLane is an automated tool which is having flexibility to generate from RTL to GDS2. Okay, so yes, it is an open source software. You can have your Verilog file along with the constraint, your timing constraint. You can have it where you can force your clock. What is a period of clock, and what are all the other parameters related to timing constraints, what we used to have it in commercial tools like Cadence and other things, Synopsys, all those things. We can load those constraints also inside this OpenLane, but uh, but it has some limitations. Okay, this has some limitations like you cannot impose your own algorithms, what you might have done, what you might have studied in your physical design, VLSI physical design course. Okay, I think most of your MTech and BTech students are studying VLSI course. So in that you might have studied something about physical design. So basically, what is a physical design? So physical design, what we used to do is uh, first we write programs in Verilog. Okay, so first we write programs in Verilog, and then we convert that Verilog program into a synthesized netlist. Okay, specific to a technology, and then after converting it to a specific technology netlist, we use uh, the, the the technology libraries. Okay, the technology libraries and the geometry parameters of the technology to go to the physical design process. So in physical design, what we used to do is we generate the layout of the entire IC. So the physical design generally starts with floor planning, power planning, placement, clock tree synthesis, and then if any optimization is required, we can perform that optimization. And then finally, we perform global routes and we test the design. The post layout verification we used to perform. Then finally, we tape out the design for fabrication. So this is how we perform this is what is happening in the basic physical design flow. So if you see in say, Cadence, yes, I hope you can see here. In Cadence, this is a basic physical design flow. So along with this, we have power planning. Okay, so what we do in power planning is that uh, we used to lay the power rails, which is required for our IC to function. It will be acting as a DC source. So this power rails will supply the power, okay, means the voltage to all the blocks present inside your IC, right? So this is what we do in power planning. Then we actually route the design by means of a special routing process, and then we place the standard cells. Then we go for a global routing, Okay, so after global routing, we perform a static timing analysis to check whether we are getting a positive slack, or ideally we should get a zero slack, but we are trying to get a positive slack. So slack, I hope the audience know what is a slack time. It is required time minus arrival time. So this we used to check. Suppose if the slack is not met, right? If we are not meeting the slack, so what we used to do is we used to change some the drive strength of some designs. Okay, so after changing the drive strengths, what we used to do is we used to see that again. We used to replace the design. Okay, means replace the entire design, means perform the placement again, so that the modules are getting placed properly. Then again we perform a verification to on static timing analysis to know whether the design is satisfying the required arrival time or not, at least to the close to the required arrival time of not. Then if things are right, then we used to go for clock tree synthesis. There we lay the clock tree network. Okay, so and we see that we are satisfying the required skew. Okay, required skew. So skew is, I hope you know, it's we may be having a different branches in our design. So between that branches, it's a difference between the delay between the branches, that is called as a skew. So basically we try to achieve that skew. We have a design, basically we used to have a design constraint that our skew should be of this much, some x value of picoseconds. So we try to get that x value of means the required value of the skew by just balancing that skew, by laying a proper by adopting a proper clock tree methodology. Like I hope you might have studied about H tree, that is very famous one, and that's the thing we will be using on that. So after this, after balancing the tree, we go for a detailed routing. Okay, again we check for whether we are getting a required timing, whether we are satisfying the required timing or not. So if not, again we try to revamp the design by using some commands, some TCL commands, what we have it in different softwares like Cadence and Synopsys. Okay, so coming to the open lane now. So coming to the open lane, so comparing this open lane with your commercial EDA software. So how do we compare is that, see, for this entire process, what I have been discussing so far, this physical design process, is you have a user interaction. You have an user interaction, like the floor planning can be done by yourself. Okay, you can do the floor plan, you can place the module by yourself, you can route the design, means you have flexibility that which metal layer you can choose. Okay, and then you have flexibility of what should be um, the congestion rate. You have flexibility on what should be the utilization density. Okay, and then you can place macro modules. Okay, you can place macros. Suppose if you have a macros in your design, okay, like PLL and other things, you can place that wherever you want. Okay, wherever you want, means according to the things, certain conditions what you need to satisfy, like the wire length, delay constraints, congestion, IR drop. Okay, so keeping all these things in mind, you can place your designs in floor planning. Similarly, in placement process, yes, here also you have your own methodology. You can have your own methodology algorithms. Okay, you can have an in-house compiler to perform this process of you can extract the content, the layout information after floor planning, and you can perform the process of placement. Okay, by using your in-house algorithm. So the in-house algorithm might be the algorithm what you might have studied in your VLSI design course or in SIG design course, right? You have a lot of algorithms for placement. So then after this, we perform, then between these, see, between each and every stage, basically you have a lot of flexibility. Okay, you can have your own methodology. You can implement your own methodology if you are using a commercial software. Okay. So, but OpenLane, what is the what we have is that we have in this OpenLane, what we are having some algorithms which is actually proven that it is showing some better results. Better results means, so how do we evaluate better results? Basically, in particularly in this field of physical design, is that we used to run our algorithms in standard benchmarks circuits like ISCAS 89, IWLS benchmarks. Okay, so some standard benchmarks we used to run the design, and we used to see that what is the performance of the algorithms. Okay, how it is giving us the output. Okay, and how it is satisfying the constraints, what happens to the side effects of the layout, okay, whether it is creating an electron migration or not. So all these things we will be evaluating. We have to evaluate, only then we can propose an algorithm. That algorithm, some kind of algorithm like that, we are actually using it in this OpenLane in each and every process of our physical design process. Okay, so apart from this, so if you take a cadence, we are you might have observed that we have for RTL synthesis we have Genesis, okay, which used to convert your RTL program to your Verilog program into a synthesized into a technology synthesized netlist. Okay, so here we have Oasis, which is again an open source. So this OpenLane is completely, it's a packed thing, which you can, from which you can get your final product, that is GDS2. Okay, this GDS2 you can get it just by loading a Verilog program. Okay, and one more thing is that in Cadence or in some other maybe Synopsys or something, so that is in that you can have you can impose some libraries which can be of any technology, like 180 nanometer, 90 nanometer, 45 nanometer. You can load it for any technology, but this is very specific as of now. The research still is going on, but as of now, till date, this OpenLane and OpenRoad, which is also available, which is also one of our open EDA software for physical design automation. So that is also, it is prone to only Google Skywalker PDK. Okay, it is 130 nanometer technology. Okay, so that's the only thing. But on the other hand, if you see, yes, you may get a very good netlist, okay, which is error free. The layout is also error free, right? And you'll be getting a very good netlist just by giving your Verilog program and your constraints. Okay, anyway, we will see that how we are going to install this. But yes, for RTL synthesis, we are using Oasis, and for static timing analysis, we are using the OpenLane uses OpenSTA. Okay, so there are also other softwares are available called as OpenTimer. Okay, you can also use that, but this OpenLane is very specific to it is embedded with OpenSTA. Okay, so again, finally, this after DFT, it comes to a DFT. Again, it used to perform that DFT by using iVerilog. Again, it is an open source software. Maybe you might have gone through that in some of our in the previous days of lectures. Some of our faculties, expert members might have taken you how to perform this DFT using iVerilog, system Verilog, and then that comes your physical design process. So for then here we perform floor planning, placement, clock tree synthesis, and then we optimize the design. Here we are the OpenLane uses iterative optimization, but there are still a lot of research is going on how to optimize the each and every process of the physical design in the OpenLane by using some dynamic algorithms like deep learning and machine learning and other concepts. Then finally, after global routing, after clock tree synthesis, for clock tree synthesis, again, they used Crayon CTS, okay, which builds your clock tree based on your H tree, okay, based on a H tree, which is a very latest research work they have embedded. I think it got published in somewhere around 2016 in IEEE transactions on very large scale integration. So you can refer that also. So they have embedded this here inside this CTS. So then, as I told you earlier, yes, they are performing iterative optimization. Maybe you can see that when I'm running the open lane today. So then they used to perform, they used to use global routing. They perform global routing by using a routing algorithm, a very famous routing algorithm. Then again, after routing this, they generate the netlist again to perform the um, to, to perform whether the layout is equal to to perform that verification of the pre-layout and post-layout, whether it is having the same characteristics or not, functionally as well as mostly functionally, and as well as the technology specific also. So this is how this open lane basically it functions. Okay, this is how the tool flow is. So yes, for layout, for viewing the layout, yes, it has you can view the layout here by using two softwares. One is KL layout and other one is Magic. So yes, for when you load Magic, I think Magic VLSI, it is given by Open Circuit Design community. So yes, you have to load the 130 nanometer Skywalker PDK while you are running your Magic. But for KL layout, it is not necessary. We can directly, once the GDS2 is generated, you can directly load the GDS2 in the KL layout so that you can see the output. Yes. So this is a complete platform of a complete automation platform. Okay, for generating your GDS2. So now we will see about how to install this open lane. Okay, so yes, we can install this open lane in two different in any operating systems you want, but it is actually prone to Ubuntu. Actually, it is prone to Ubuntu. So if you are having any other operating systems like Mac operating systems or Red Hat Linux, okay, then you need to have those libraries. Okay, then you need to have those libraries. Only then you can install this. Or what you can do is that you can have a, I think most of you are having a Windows operating system, so it is better you can have a virtual box and you can have a VDI for Ubuntu. So I would recommend that Ubuntu, the latest version 20, which has a lot of updates with respect to the libraries that we actually require to run for this open lane. And one more thing is that you need a special software called as Docker. Okay, you need a Docker here because there are some libraries they have installed it in a Docker. So you can once you pull the Docker, it will automatically puts that particular libraries inside the container. Okay, inside your container where you have your open lane repositories. So after that, you can easily pull that open lane from your Docker using your Docker. Then you can have some commands to run the open lane. So these are some of the steps. So for those who are very new to this Docker, these are all some of the steps. You can make use of these steps to run the application, the Docker application. Okay, you can make use of these steps, and these steps are again there are a lot of other this is the steps what is being commonly followed for installing Docker. But yes, suppose if you hang up anywhere, some may be using a different laptops, maybe of different memory size. Okay, so I have installed this Docker in our computer systems which we are having in our college SRMIST in i3 processor with 4 GB RAM. Okay, so I hope you can also do it in your laptops. And I also install the same in my laptop also with virtual machine, which is actually i5 processor with 8 GB RAM. Okay, so it is not specific that yes, you have to run it in a specific software. Yes, it will run. You can install Docker in any operating systems you want, but the thing is that you need to follow the steps. Okay, yes. So any doubts so far? Can anybody assist me to see any doubts? Any doubts so far? Shall I give a? It is better to have it as an interactive because it will be easier for me to track also.
No, sir, no questions have been put yet. So
Okay.
participants are requested, like for any sort of queries, please put in the chat window so that it will be interactive session and a two-way process of interaction.
Thank you, madam. So let me continue that. If there is no doubts, I think there are no doubts. Let me continue. So this is how we install the Docker. So after installing Docker, what we need to do is we need to clone the repositories from the OpenLane website. Okay. So what you can do is that you can go to Google. You can type. Okay, I am using Google here. Just a minute. Yeah, you can go to Google and you can type OpenLane. Okay. So OpenLane GitHub. Okay, you can search in this. So here you can see from where you can clone. Okay, the exact process. Okay. So yes, I have also given the same process in my presentation. You can see that. I hope my screen is visible. So the same process I have included. Okay, so you can have that process also. So after cloning this, okay, after cloning this OpenLane, what we can do is that you can go inside OpenLane and you can make a you can make a directory for installing your Skywalker PDKs. Okay, so after making the directory, what we can do is that we can have we can make the OpenLane. So this make OpenLane, before you run make OpenLane, you should ensure that your Docker is installed and it is in active state. Okay, you should ensure that it is in active state. So once it is done, you can run this make OpenLane, then which will clone, or I can say which will pull the OpenLane image. After that, you can just make a test. Okay, make a test of they have a testing. They have written a code make file to test the existing designs. Some of the existing designs in their in the OpenLane directory. So you can test that, and you can see whether the OpenLane is running or not. Okay, so this is very important. First thing is you need to clone. Okay, you can clone it by using the steps what I said. Maybe you can follow the steps what is given in the OpenLane the GitHub, or you can also use the one what I am sharing here. Okay, the same, both are same. Okay, both are same, but here I have included a specific branch. Yes, it is working with the existing branch also. Okay, so yes, it takes time. Okay, it takes time to install. So it took me around 1.5 hours. Okay, to just download. Okay, to make OpenLane ready, OpenLane alone to get ready with my laptop. So you can try that, but anyway, for I'm just skipping those installation because maybe I have some videos on that installation process. I will share it to the host of our EICT Academy. So you can see that videos also. Okay, and yes, after installing it, what we have to see, what you can see in that. Okay, so you can see there are some designs. Okay, there are some designs. So once you done with the make test procedure, okay, once you have done with the make test procedure, you can see the design has OpenLane already has lot of designs. Okay, so you can see it is DES, AES, PicoRV, ES, ES Core, S44, SPM. Okay, so like that, lot of designs are already existing there. So, but they are running this OpenLane for testing whether the user you need to know, right, whether the OpenLane is working fine or not. So they have written a make file to test the open lane is working or not for the design called as SPM. Okay, for the design called as SPM. Again, this SPM is a IWLS 2005 benchmark circuit. Okay, you can download it from internet, IWLS benchmarks also. So, but yes, you can, after downloading, after running this make test, you'll be your SPM will be running. Okay. Yes. Apart from this, I was telling you in the previous slide that you can give your own constraint file, just like your commercial EDAs like Cadence and Synopsys. So yes, you have a special directory over here, okay, called as config.tcl. Okay, so here you can see we have given the design name. So this design name, they have given it as SPM. So this SPM is nothing but the module name, okay, the Verilog module name, what we have it in your design. So you have SPM, you are loading SPM here, means it doesn't mean that you are loading the folder, you are loading the module name, the Verilog module, the top level module name of your design. Okay, and then you are setting the location of where your Verilog file is present, and then you are giving the clock period, and then you are giving the clock port of the design, and you are giving the cell pads, how many cell pads to be placed in each and every sides of the core area of the IC, and then you are also giving instructions, okay, on which technology library you are supposed to, the design has to be implemented. Okay, and apart from this, yes, you have some flexibility in configuring the location of the pin, right, by means of file extension .cfg. So here you can configure the location of the pins. So pins means you should know, you know that very well. If you're writing a Verilog program, you'll be having some inode ports. So those inode ports now it will be acting as a pins now, input output IOs for your design. So after doing this, you can see the RTL description present inside your sorry, present inside your folder called SRC. Okay, maybe I will go to the next slide. You can see that program running in the present in the SRC. So after you load the design, after you complete make SPM, what happens is your design will be loading, and it will be passing all the phases of this physical design, all the phases of this entire process what I have been explaining. So like synthesis, timing analysis, floor planning, placement, clock tree synthesis, optimization, routing, okay, again extraction, again verification of post layout synthesis, finding out IO drop in the power delivery network. Okay, so all this entire stuff will be taken care of by open lane, and finally it will give you a layout, okay, like this what you are seeing in my presentation. Okay, so yes, like your commercial software, here also you can see, you can take report of your designs. Okay, what are all the things you can take report. Okay, so you can take the reports from this location. You can see reports are, there is a folder called as reports. So here you can see there is a CSV file telling you what is the entire design summary. It is telling you the entire design summary. Yes, I will open all these things for your reference. You can see that when I'm running this software. So here you can see what is the cell density we have used. Okay, what is the core utilization? How many number of standard cells you have used? Okay, what is the half perimeter wire length? What is the wire length? Okay, what is the clock skew? How many number of clock buffers? Say for example, when you synthesize the design, mostly if you see in Genesis or RC compiler, you'll see what are the different types of logic cells you have, okay, with the different drive strength. So that also you may see here, okay. And then you may also get the power report, okay, switching power, all these things you can see it here, okay. And in each and every folders of this open lane, you can see what are all the reports you required. Say for example, if it is placement, you will find out what is the density, how much is congestion. Okay, I think some congestion they have included recently. Floor plan means they will you can see what is the modules are, how many modules are being used for a floor plan. Okay, how many modules are placed. Then you can see any errors with for the layout versus schematic. Mostly it is very difficult in commercial software. Okay, performing this layout versus schematic. You have to perform. You have to extract the spec file and then you have to do it. But in OpenLane, you can do it in a single step. Okay, in a single step you can do it. Okay, so these are all the some of the reports you may be getting from the OpenLane after running a not only this make test, after running any designs. After running any designs, these are all the some of the reports you may get. Okay, apart from the layout, right? So yes, so all these things I have used the repositories. Yes, and I have shared some of my practical practical outputs. So I will show the demo also here. Yes, any doubts in this? I think I have completed with OpenLane. Any doubts, audience? Yes.
So no doubts are posted yet.
Okay. Okay, fine. So shall I continue with the demo?
Participants are requested to please respond in the chat window. Please respond. Participants. No doubts, sir. Like one of the participants responded. Yeah.
Thank you. Okay. So if you have any doubts, please let me know. Okay. Okay, then fine. So then I think I can go with the demo, right? Fine. So hope you are able to see my screen.
Yes, sir.
Yes. Yeah. So I will open terminal now. Okay. So yes, as I was discussing, I have already installed the OpenLane because it's a time-consuming process. As I discussed, yes, we need to have to install Docker. We need to clone the repository from the GitHub. Okay, so all these things I have done just to save your time. But now I will show you what are all the things we can see from this OpenLine. Okay, so yes, I am running into Ubuntu 20, the very recent version of Ubuntu. Okay, so first I will go to the location where I have installed OpenLane. So you can see I have installed OpenLane here. Okay, you can go to the location from where you are going to execute the OpenLane. And inside this OpenLane folder, you can see there are a lot of files are there, some folders are there. So I was discussing about the designs. You can see the designs, the inbuilt, the example designs, okay, which is present inside this folder called as designs. Okay, a lot of design files are there. But as I told you, you need to make this PDK library, what I am showing here. Okay, just make an empty PDK library. After making this empty PDK library, as I was discussing, you can, after making the make OpenLane, okay. Hope you are able to see my screen. Any interruptions?
No, sir.
Yes.
No, sir. The
Thank
screen
you.
is visible.
Yes. So as I was telling you, yes, after making this make OpenLane. So before we type the step make PDK, what we are supposed to do is that we need to just make a new directory called PDK. Then after that, we need to go with this step called as make PDK. Okay, then we need to go with this step called as make PDK. So before going to this make PDK, we need to tell this OpenLane compiler that where we are going to make PDK. So for that, you are going to type this command called export PDK. Okay, PDK underscore root. Okay, to tell where this PDK is available. Okay, so yes, to know what is the location of PDK, what you can do is that you can go inside PDK by typing the command cd change directory cd PDK. Okay, which will go inside the PDK location, and you can type PW, okay, to know the location of your PDK. Okay, then you can come out of PDK, okay, by cd dot dot, okay, cd dot dot you can type, and you can come out of PDK. Then you can type export PDK underscore root, and you can simply copy paste this location. Okay, and you can simply copy paste this location, so that you are telling the compiler that this is a location you have PDK, and this is the place from where you have to take the library and generate the netlist and do all the process for giving the GDS2 of your layout. Okay, so this is how it does. This is how it goes. After doing this, what we used to do is that according to our design procedure, according to the design procedure given in our repository, what we need to do is that we need to test the design. So testing the design means you need to test the designs which is present inside your the folder. Okay, so let me go inside the designs folder and show you what all the designs are already existing. So you can see here there are some designs, like as I told you, AES core S44. Okay, and you can find SPM. Okay, you can find SPM. So SPM, yeah, it is here. So SPM is the one is actually linked for making the test, or I can say for testing the OpenLine. Okay, so you can see after after typing make test, you can see it will create a it will perform the OpenLine design flow, and it will run the entire design things. Okay, so now what I'll do, I'll just go inside the design and I'll show you what all the design files that SPM has. Okay, so just a minute, I'll clear everything. I'll show you. Yeah, so these are all the things that SPM design file has. Okay, so you can see it has a Janssen, it has a config.tcl, it have runs. If you have already run, this runs folder will will have all the results of runs. So you can run this design multiple number of times. If you run multiple number of times, you will get different folder with that particular date when you are running, the time when you are running. So I'll show you some of that copies what I have done. So define cd runs. Okay, so I have run it in 2 times, tested this. So this is how it is. So apart from this, you can see there is some files for loading your Skywater 130 PDK. So you can see there are some different definitions of Skywater PDK. You know that if you are taking a technology library, you know that there will be 2 different types of library. One for the library has basically it has um, low power cells, high power cells. Okay, and you have separate cells for IO pads. Okay, so all these things you will have if you are having it for inside a library, inside a technology library. Yes, but here they have made it as a separate library. You can see for each and everything they have a separate library. Okay, for each and every process they have a separate library. Right, so now what we will do, we will get inside that configuration file and we'll see what the configuration file has. Okay, so I will open through gedit config.tcl. Okay, so yes, it will open the gedit. You can see the design name, okay, SPM, and the location of the Verilog file, and the clock period, and the clock port name, and the how many number of pads I am supposed to have. Okay, and this I have commented because you can have your own pin configuration, and here you can see that this is the configuration file, and we are using the technology file, what it is called as your Sky 130 PDK. Okay, so this is how it is. I'll show you the file, the pin configuration file also. I will explain you how the pin configuration is also being done in this. So here you can see you have #n, #s, #e, #w. So this NSEW refers to north, south, east, west. Okay, so they have placed the pin X in the north and reset pin in the south, clock pin in the east, and a pin called as P in the W, means in the west. Okay, so like this you can also place the pin as you want. Okay, you can reorder the pin, you can edit the pin, this file, and you can save this file. Okay, and you can save this file. So after everything is done, so we can go inside, we can go out of this location, and we can type. First we need to load the means the open line. Since I have already ordered the means I have already loaded the open lane, I have pulled the open lane. So if I do that process, it will be more time consuming. So I will once your open lane is, I will do a process which is to be done once you have loaded the open lane. Okay, so once you have loaded the open lane in your Ubuntu system, what you are supposed to do is that first thing is that you need to make a directory to tell where you are going to have your PDKs, and you need to export the PDK routes by using this command. 1 minute. By using this command, you need to tell where the PDK lies, and then what we are supposed to do is that we need to mount the open lane. So the command to mount the open lane is make mount. So once you mount this make mount, so it will mount the open lane. Okay, so it takes time. It purely depends on the speed of your internet. Okay, so once it mounts the open lane, what we need to do is now you have to run your designs what you are having inside your the designs folder. Okay, so but what I will do now is I will just run the first I will run the make test. I'll show you how it generates the layout. Then I will take a design from an example design from the designs folder, and I will show you how to run it by mounting it from the open line. Okay, so now I'll type make test to run open lane. So it is automatically mounting the open lane. So you can see here it is mounting the open lane, and after mounting it, it is loading the open lane. Hope all of you can able to see my screen. Yes, all of you can able to see my screen. One of you please respond. Yes. So after loading the open lane, yes, you can see what all the things it is loading. It is loading our configuration file. It is loading the definition for the standard cell library, and it is loading the metal layers. Okay, yes, it is performing the synthesis here using the Liberty files, the library files, and it is performing the floor planning. You can see the core area and width 7.86 and the height is 87.04. Okay, and you can see what is the power grid size. Okay, the pitch of the power grid. Okay, power grid network, horizontal and vertical. Right. Yes, are you able to see my screen?
Yes, sir, the screen is
Yes,
visible.
yes, thank you, thank you. So yes, it takes time, it takes time to run because it is a very big design. SPM is a very big design. So you can see here what are all the things it has performed. It has done the power grid, and then it has a IO placer. It places the IO, and it gives you a def for your floor plan. Okay, it is generated the power grid, and it is performing global placement. Okay, after global placement, it is performing optimizing the design by resizing the design. Okay, by using a optimizer. So this resizer, what it will do, it will resize the standard cells so as to satisfy the static timing. Okay, first it will automatically it will do. Then it runs the static timing analysis to see whether the design is satisfying the static timing analysis, static timing constraints or not. That is your slack time. Okay, so every time it performs iterative optimization. You can see the index. Okay, this index is nothing but the number of times it is optimizing. So it is, you can see still it is running for 22. Okay, so every time it is extracting the design and it is calculating it. So it is calculating the power. Okay, it is streaming out the GDS. Okay, so it is generating the GDS for viewing us in KL layout software. Okay, yes, you can see that it is generating the left file library exchange format, and it is performing LVS also. So it is checking whether we have any mismatch with the layout versus schematic. Okay, and then here we can see there are no violations, and it is generating the summary report for us. So now you can see here it has completed all the designs, all the steps what we have been discussing in the open lane design flow. Okay, with the different iterations. Okay, with the number of iterations, 39 iterations, and it is telling us that there is no errors. There is no errors in the magic layout, and there is no LVS error also, which means that our layout as a schematic is fine. Okay, and then number of pins violated and number of nets violated is also 0. So usually when you do it in a commercial software, it will tell you what is the violations, okay, warnings and error. But it is as it is an iterative optimization, so it does by itself. Okay, but when you are doing it for a very big design, even big design which are more bigger than SPM, it may take a lot of time. So that means you see that how much time how simple is the SPM design is, and how simple is the open lane is also. Okay, so you can see the flow is completed in just 4 minutes and 24 seconds. Okay, which is really a challenging thing for the commercial EDA. Okay, now we will go inside our designs folder to see what are all the things it has generated inside the SPM folder. So yes, we are in SPM folder now. So I will clear my screen just to make nice visibility. So yes, I have cleared the screen. So yes, the design is actually available in SRC folder. You can see Verilog file is there. Okay, you can see Verilog file is there. Here you can open this Verilog file by using the command gedit, or you can use nano also to open the file. Yes, it is opening. This is a Verilog file of your SPM design. and we have timing constraints. Apart from the clock, we should also have other constraints, right? So that is also available here in this folder, spm.sdz you can type. So you can see what is the name of the clock and what is the period. So this period, what you are giving, that should match there. Okay. So otherwise it may report some error. So that is a thing. Now we will get inside the report. All the reports we are getting from OpenLine. Okay, we are getting from the OpenLine. Yes. So to see that reports, you have to get inside the folder called as runs. Okay. So after that, you can see, as I told, I have done a lot of runs. Okay, today morning, this is my run. Okay, this is the OpenLine test run. So what I have done it now. Okay, so I will open that OpenLine test. Okay, and we will see what are all the things we have. So you can see that it is having reports, results, and some temporary. So this temporary is to load to have those temporary results what we are getting. Okay, so OpenLine uses this folder to have this temporary to perform some task to or I can say to get some information from file and perform some task. Okay, to give us a very nice report. Okay, so it is using this temp folder. So apart from that, the very expected thing is that our results. Okay, so results you can see in the results folder. Okay, sorry, results folder. So here you can see the results of each and every stage of your physical design process. That is from synthesis, placement, synthesis, floor plan placement, uh, CTS, and then routing, and then you can see for viewing the layout in Magic as well as in the KL layout. Okay, so we will go inside. We'll go inside the KL layout editor to see our KL layouts. Okay, to see our layouts, SPM design. So KL layout is not coming with. Basically, it is not a repository included inside the OpenLine. Yes, we need to install this KL layout separately. You can download this from the website klayout.de, I think. You can type KL layout. Yes. So this is the website. You can download this. Okay, for your version. My version is Ubuntu 2020. So I have downloaded this. I am just installed this. Okay, now after installing this, you can view the result of you can view the layouts. Okay, from getting inside, I will get inside the KL layout folder. Okay. Okay, I'm getting inside layout KL layout folder. Here you can see there are a lot of left files, GDS, LYP, GDS for XOR, and then XOR XML is there. Okay, means that it is having some XOR files. Okay, XOR as a standard cells. Now to see the layout of this SPM, okay, you can run the KL layout editor means the viewer from the terminal of your Ubuntu itself. You can type KL layouts. Okay, you can type KL layout spm.gds. Okay, and press enter. So it takes time. It's again purely depends on the system what you have. Okay. So this is the layout. I hope all of you are able to see the layout. One of you please respond.
Yes, sir.
Yes, yes, thank you very much. So yes, this is the KL layout. This is the layout of SPM design. So you can see the IO pads are located here. You can see the IO pads. Okay, right, and you can also see the standard cells. So what is the difference between this layout editor and the layout editor what we have in our commercial software is that there you can see you have options to select the nets. Okay, here if you see in Cadence or Synopsys, you can select the net, but here you need to it is little bit difficult. So alternatively, what you can do is that you can go to the particular process and you can view the layout. So I'm now in KL layout. So what I'll do, I'll go and come out of this and I'll go to the floor plan stage. Okay, to see my floor plan. So you can see spm.floorplan.def. So from here you can open the layout of the SPM in floor plan stage. spm.floorplan.def. So def means design exchange format. I hope most of you know this. So it is a standard cell-based design, so it does not have any macros. So you can see different metal layers have been used to do this, right? And then you can go inside the other parts also, like placement. I'll go inside placement. Sorry. Okay, so I'll go inside placement, and I will see the layout of placement. Layout till placement process. Okay, so this is a placed design. So you can see the power grids. Okay, so this black color refers to metal 5. Okay, metal 1, and this blue color, I think it should be metal 4. Okay, and you can see the special route is also be done. Okay, it is run, right? So like this, you can see each and every stage. Okay, in each and every stage of your report, you can see results. You can see what are all the reports you are getting. Okay, now we will see what are the other things we can get it from this open lane. So you can get reports. Okay, you can get reports. So for that, you can go inside the reports folder, and you can see what are all the reports you can get in each and every stage of your physical design process. Okay, so let me go to the floor plan, CD floor plan, and you can see a report on what is a core area. Okay, Verilog to def when conversion, what is a core area, what is a power grid, power delivery network report. So I will open one of the report. So 3 hyphen Verilog to def core area dot report. So this is the core area. So it has 4 parameters. Yes, it is left bottom, and then right left no left bottom, and then right bottom, right top, and other things. Okay, so it's like a rectangle. So how a rectangle dimension you will give, in the same way it is mentioning the core area of the floor plan. Okay, so then we will go inside placement. So CD placement. You can see a lot of reports are available in placement. Why? Because placement is not a single process. It runs along with the the clock tree synthesis. So because you need, sorry, it runs along with your STA. Okay, so yes, STA. Why placement is related to STA? Because you are refining the placement. If you are not satisfying the STA, means the modules present inside your placement. Okay, modules present inside your layout, if you are not satisfied with the STA. So you can see there are different reports are there. You have 14 reports, and I told you, right, it is running optimization. Okay, concurrently it is optimizing. Iteratively it is optimizing the design. So every time it checks for static time whether it is satisfying the required slag or not. Okay, so I will open any one of the report just to show you. So I will open 8 minus replace STA dot true negative slag report. So you can see that there is negative slag is 0. Similarly, you can see the worst case negative slag report. So the worst case negative slag is also 0. So this is after replacing the standard cell. Okay, so we will also see the design, the reports after clock skew also. So I will open gedit 9 hyphen resizer dot sta clock skew report. So you can see what is the clock skew report. You can see what is the latency. Okay. I think actually the same way how we get it in commercial software, we are also getting the same way. Okay. So the first column is the name of the clock. Next will be your latency and CRPR, and then your clock skew. So this is your clock skew. You have two branches. So this is your clock skew in the branch. Okay. So then we have STA reports also here. So STA timing reports we'll see. Okay, so we don't have any paths, violating paths. Okay. So complete STA report also we can see. Okay, again, if there is any violation, it will report here. Okay, so these are all the some of the reports we can see. Okay, still there are many things we can you can explore that. Okay, after you install the OpenLine. Okay, then after after your CTS, also you can see what are all the reports you can get it from CTS. Yes, as I told, it is a iterative optimization. So we will open gedit 12-cts.rpt. So you can see that what is how many clock routes you have, how many number of buffer nets you have inserted, what is the subnets, how many sync nodes are there. Okay. But I think we cannot see the clock tree. I think that is the only thing I hope. Okay. So all together you can see it in a runtime summary report also. Okay, which will tell you what is the runtime. Okay, then we have final summary report also. Okay, final summary report, which I would like to open not through this terminal because I'm showing it in Ubuntu. So I will open the folder where I have this content and I'll show it from there. So I will open SPM runs OpenLane and reports. This will have a final summary in .csv format. So I'll open in CSV means even you can open it in Excel also. Okay, but in Ubuntu we don't have Excel, so we have this only. So I'm opening this. Yes. So here you can see what is the name of the design and flow status, how much time it takes, what is the routing time, what is the core area, what is the die area, how many cells you have. Okay, what is the memory usage for running this, what is the cell count, and as I told, for routing we are using Trion routes. Okay, then we can see the violations, antenna violations, what is the wire length, so how many wires have been used. Okay, then half perimeter wire length. I hope many of the students might have studied this in ASIC design as well as VLSI design. Half perimeter wire length. Then routing layer 1, layer 2, what is the how much routing resource is being used, and wire bits. Okay, then cells, which we got it from the ABC synthesis, means your logical synthesis. Okay, how much cells we used. Okay, you can see we are using 4 SPM takes 4 mux of 97 inputs, outputs, level, N capacitance. Okay, we use N capacitance for reducing the drop in the design, IR drop in the design. So N capacitance, tap cells have been used and diodes have been used. I think I know most of you know for what purpose, latch up issues. Then physical cells, the clock frequency. Okay, the suggested clock period, and what is the clock period we have, and fan out aspect ratio, and this is floor plan power delivery network vertical pitch size, and similarly horizontal pitch size, target density of the power plant, and what is the net library we have used. Okay, so Skywater HD we have used, cell pads, and then diode insertion strategy. Okay, so these are all the summary reports what we will be getting from the open lane. Okay, so this is how we can run a test. Okay, we can test the open lane whether it is running or not. Okay, so apart from this, we can suppose if you have any designs. Okay, apart from this, if you have any designs, you can load the designs. Okay, inside this folder. Okay, with the contents what we have seen just now. Okay, say for example, if it is SPM, or let us not take SPM, we'll take S44. So inside S44, you can see what all the things are required. You need to have this configuration file. You can just copy paste this. For power delivery network, you can tell what is you can edit this power delivery network configuration file. 1 minute. Okay, you can edit this power delivery network configuration file. You can see instead of metal 1, you can also say I want to use metal 2. So like this you can edit. Okay, and see here they have mentioned what is the metal layers they need to use. So you can also use a specific metal layers also by just removing one of the metal layer or changing it to anything, right? So and then you can have your SRC. Okay, SRC will have your Verilog program. So you can see, I will go to SRC. You can see that there is a Verilog program is there. So it is your S44. You can have it here for your design. If you have any designs with you, you can load it here. Okay, and you can go inside the configuration file as we did. Gedit config.tcl, and you can change the clock frequency. Okay, configuration. So here you can see in the previous SPM we have the clock name as simple CLK, simply as CLK, but here we have the clock name as config_clock. That's how it's different. So here you can see the placement density. We have given 50% placement density and floor plan utilization as 50%. And yes, we are including power delivery network, and yes, we are having a clock period of 30. Here the design name is kept as LUT_S44. So that is a top level module name. Okay, so now we will see how we can run this. Okay, how we can run these design files. Okay, let us assume that you have loaded a design inside your design folder with all these configurations, with all this environmental setup, like your libraries, your configuration file, your power delivery network file, and then your Verilog programs also. So let us see how we can load this. Sorry, how we can load this in our. Okay, how we can load this design in our open line. So now I'll come out of this designs folder. Now what I'll do, I will type, if I'm planning to load some other design, okay, which is my own design. It can be anything, right? You might have done a research, or you might have done a project. You might have written a Verilog program. For that, you need to see a layout. Let us assume, right? So you can do that by just not typing make test. You can type make mount. Okay, inside your open line folder. So it will mount your open line first. Okay, so it just takes some time. Yes, now it loaded the mount. So you can see that once it has been mounting the open line, it is coming inside the bash of your open line. Okay, so now what you have to do, you have to type the command .flow.tcl. Okay, which is the command to run all the physical design process of of your design. Okay, then you need to choose the design, which design you need to run. Okay, so here you need to give the top level module name. So I have given flow.tcl to run. I am just giving instruction to my open line to run the open line. Okay, to run all the physical design process of the open line, and I am choosing my design by typing -design and the type of the name of the top level module. So here I am giving S44 as my name of the top as my design. So you can see what is happening now. So yes, it is loading the open lane. Hope all of you are able to see my screen. Are you able to see my screen? All of you, please, one of you respond. Meanwhile, if you have any doubts also, you can ask me.
Yes,
you
sir.
can
Yes,
see
sir.
the
The
power.
screen is visible.
Yes. So you can see the power report has been generated a few minutes back after synthesis. Okay. As I told, it is checking what is a skew, what is the slack, whether it is met or not. So if it is not met, what it performs, it again go for a resynthesis resizer because it is using a Trion CDS. So sorry, open timer for performing this STA. So you can see floor planning has been done and it is generating the clock. You can see what is a power grid. Okay, it needs to be minimized, so it is going for informatic minimization. Okay, you can see how many technology layers, how many vias is being used during this stage. Okay, so it is telling us what is the width, the recommended width and pitch of your rails. So yes, it is taking some time to generate the violations of from the power delivery network. So the worst case drop, right? So our supply voltage is 1.8 for the 130 nanometer. So the accepted means 130 nanometer. If you are having a power delivery network, you can have a 10% or a 15% drop in your from your power delivery network, which means if I am supplying a supply voltage of 1 volt, I can accept till I can have a drop till 1.9. Okay, I should not have a drop less than 0.9. Okay, which means that my maximum power is not getting transferred to my modules present in your design. So if my maximum power, which is 0.9 is not getting transferred, then definitely my design will not function properly because it is not getting the required DC voltage. So it won't function. It may fail in in many places. So that's the reason why we are generating this IR drop analysis also. So you can see here, it is not thinking about congestion. Okay, it is not thinking about congestion. That's the only thing. But the congestion, for optimizing the congestion in the, yes, it is giving some congestion report, but the congestion report when compared to the existing commercial tool, it is a little bit, it is somewhere, it is deviating. Yes, some research needs to be done there. I think the community is still working on this, and you can see what is the the constraint for the clock. We set 30, and the config.clock is our clock port. You can see what is the transition, what is the uncertainty. So all those stuff you can see here, and then you can see what is the timing parameter we got. So placement has been done. So it is optimizing the slack, the negative slack. So once there is no violations, so you can see what is the skew it is. By default, it is 0.03 picoseconds, which is very, very small. Again, after optimizing it, you can see what is the report uh, on power. Okay, sequential, combinational, just like how you see here in our commercial software. Then we can see half perimeter wire length, and it is after doing after optimizing the design, it will regenerate the clock and our STZ constraint. Okay, you can see how the clock tree is being propagated. Then we do Trion CTS for global routing. Then again, it is checking for timing. So once everything is done, it is writing the Verilog file for performing layout versus schematic verification. So you can see that the def file has been created along with the SDC. So along with the constraints, the timing reports and other things. So yes, you can see that it has completed all the process, just like how we checked for SPM design. Even for S44, it has completed without any fatal errors. Means without any warnings and without any errors. Okay. So after this, yes, just like the same process, we can see the layout of the design by getting inside the folder of S44. So we'll get inside the designs folder. Sorry, designs. So I will clear the screen to have a better visualization. So I'll go inside S44. Then I'll get inside runs. I'll choose the one which I have done it today. Okay, it is 28th. So it is CD run and with today's date. CD run 28. Then as usual, you can see it is giving us the results and reports. So I will show you the layouts. First, I'll go inside the results. I'll go inside K layout. Okay, I'll show you the GDS of S44. So K layout, UT, GDS. Yes. So this is the layout of S44. The GDS2 layout means after completing the entire design process. Okay. So this is how we have to use OpenLane. Okay, if you are having your design, if you are having your own design, you can have your layout without any flaws. But only limitation is that it is specific to Skywater 130 PDK. Okay, it is that specific, but the team is still working on to clone with to have the other PDKs, whatever the recent PDK, that is the technology files what we are getting, like 7 nanometer, 45 nanometer, 14 nanometer, and all those things. Okay, but as of now, it is very limited to 130 PDK. Okay, so yes, I think any doubts? If you have any doubts, you can ask. Any doubts, participants? Any doubts from participants?
Yeah, so participants, if you're having any doubts, please post in the chat window. We are not getting any doubts today. Please post your doubts. At least respond something. Even if you're not having any doubts, please respond in the chat box. So no doubts from the participants, sir.
Okay, thank you, ma'am. So we will go with the next thing. What I have planned is I am planning to teach the queue flow, which is another open source software for generating the layouts. Okay. So please let me know whether my screen is visible or not. Just a minute. Okay. So I'm sharing my content. Yeah, is my screen is visible?
Sir, not yet. It is showing us it's starting to share content. So like, are you sharing the whole screen or any particular application you are trying to share, sir?
No, I'm trying to share my presentation.
Okay, so can you please try once to just share your whole screen and then open the
Okay.
presentation
Okay.
slides? It might work. I'm not sure about it.
Yeah, I think it is it okay now?
No, sir. It's not.
Because
It's not.
I'm sharing my entire screen now.
No, sir. So, but in the
It is
morning when
showing.
you tried, sir, at that moment it was coming, but now no, it's not coming, sir. It's showing us it's starting to share content.
Okay. Ma'am, to, whether we are having a break, maybe I will change my internet.
Yeah, so we are having break from 12, but like if you want, so we can give the 15 minutes break now, and we can 15 to 20 minutes break, and we can start the session by 12. Whatever you
Okay, ma'am.
suggest.
Okay. Yeah, that is fine.
Yeah,
Maybe I can
yeah,
change my router, and I will join by exactly by 12 o'clock. Okay.
yeah. So instead of
So we will
12:15,
have
we'll be starting by 12.
by 12. Yes, yes.
Yeah.
And we'll
Okay.
have a session
Thank
on Q flow. So what are all the things we
Yeah.
can have it on Q flow? Yeah.
Thank you, sir. And
Thank
thank
you,
you all
ma'am.
the
Thank you.
participants. Participants, please do not get disconnected. So today we are taking the break a bit early. Instead of starting the session at 12:15, we'll be starting the session at 12. So kindly join by 12. Hello, Srinath sir.
Yes, madam. I'm not able to share the screen.
So you're not able to share.
I made you presenter. Now you should be able to do that.
Srinath sir, can you please check now if you're able to share your screen or not?
No, madam, I cannot able to share.
Sharing rights has been given to you, ma'am, sir. Like still you're unable to share?
Yes, I'm not able to share. I am not able to share this. No, previously it was fine. At least I find something over my name, but now even that is not there. Shall I connect again?
Yeah, probably, Srinath, that you can do it. Sometimes what happens is that when you log out and log in, right, it works. It happened once for me. You can try it out.
Okay, I'll just come out of join again.
Yeah. Okay.
Hello, Abhinandan sir.
Ma'am, I think he is trying to rejoin, ma'am. Let us wait for a minute and I will ping him.
Okay, okay, sir.
Because last time also I had the same problem. Once I log out and log in, it worked for me. So let us wait for 2 minutes and then I will ping him.
Okay, yeah, Srinath sir has joined, but I guess like his audio is not yet connected. So this might be
Yeah,
because of
probably,
internet issue
probably
also.
you need to make him a co-host or something like that, ma'am.
Yeah,
Last
that
time
can
it
be
even.
made. Yeah, that can be made, but his audio is not connected yet.
Okay. No, ma'am, you should you should enable it. It seems.
No,
The
no,
first
no,
time for
no.
Arjun it happened.
No, we can't enable at our end, sir,
Okay.
because his audio is not connected only. We are not having the audio symbol
Okay.
behind his name.
Yeah. Yeah, he messaged me. He's actually having some trouble trouble logging in. He is actually trying it.
Okay. So participants are requested to please stay connected and wait for a few minutes. We are trying to resolve the issue and the session will start soon. Yeah, so your screen is visible now.
Okay, thank you.
Yeah.
Sorry for the inconvenience. I have a network issue here. Yes, coming back, we are today we are going to see the next session. It is on Q flow. So morning we have seen what is the how the open lane works. Okay, so now we are going to see about Q flow, which is another open source EDA used for generating the layout. It's it's an automated layout generator. So that is called Qflow. So basically, this is actually given by Open Circuit Design. Okay, the community called as Open Circuit Design community. So they have given this Qflow. It is not specific to a particular technology. Yes, you can have this for any technology, like 180 nanometer, 45, all those stuff. Okay, so whatever technology you have, you can library. If you have technology library, you can perform this. You can use this Qflow, and you can perform the. You can get the layout. Okay, but what is the one drawback in this Qflow is that it has some limitations in timing constraint, which means it runs the entire design for a specific timing constraint, not for the timing constraint given by ourselves. Okay, so you cannot impose any timing constraint in Qflow, whereas you can do it in OpenLane. That is the only difference between OpenLane and Qflow. And one more difference you have is that in OpenLane, it has the ability to handle the macros. Means you can floor plan the design. Okay, but here it cannot handle the floor plan. It takes only even though it synthesizes each the modules inside your Verilog program as separately, but it has the flexibility. It can do only as a standard cell based design, not as a macro. Okay, that's the only thing. Even though you have a separate module inside your Verilog program, it converts it into a standard cell based design only, not as a separate macro. Okay, so that's the difference. That's the two difference. First thing is that it runs only for inbuilt timing constraint, and it is not specific to macro based design. It is specific to only standard cell based design. That's the only difference. Yes, again, this Qflow is having its own, just like your OpenLane, what we have seen today morning. It is also using for logical synthesis. It is using uh, Oasis software, and for placement, it uses Grey Wolf. Okay, and for routing, it uses QRoute. Okay, an algorithm called as QRoute. And then for static timing analysis, it uses the Vesta. Okay, it is again an algorithm developed by the same community, and they have embedded all these things inside the Qflow. Yes, you can install this Qflow in Ubuntu operating system. If it is a very latest one, you can just use these commands. Okay, you can use this commands what you are seeing in the screen to install the Qflow. So it is very easier. Just it may suppose if you are not using the latest version of Ubuntu, maybe you have to clone that Qflow from its GitHub repositories, and for that maybe you may have to install some libraries for that. Okay, that's the only thing we have. Okay, so now I will show you the demo on how we can run Qflow here. So first I have installed it in my Windows operating system. Please let me know whether my screen is visible or not. I'm starting my Ubuntu in virtual machine. Is my screen is visible?
So now a black screen is coming where we can see your cursor, that you are moving your
Okay.
cursor, but nothing else is visible.
No, I'll share it again, madam. Okay, இது வரட்டும். Just a moment. I'm just loading my virtual machine. In few minutes, I will share the screen. Just a moment. Yeah, I think my screen is visible. Is my screen is visible?
Yes, it's visible.
Yes. Yes, thank you. So now I will run the queue flow. So we can see here, I use the commands what I've showed you in my PPT. I used sudo apt-get install qflow. Okay, so the same command I have used in my Ubuntu. Maybe I will copy this and I will put it in our chat box so that those who want can use it and to install this. Okay, so how to run this qflow, right? So after installing this qflow, once you have cloned the repositories from the GitHub, you can find that your qflow is get installed. Okay, so you can type in terminal as qflow. Okay, just a minute. So in terminal you can type qflow. Okay, GUI, and you can press enter. So once you have entered this, so you have to you have an option of selecting which technology you want to work on this. So this technology, it is present already in that library of qflow. If you are inserting, if you are doing it for a new technology, maybe you need to copy that required technology file inside the location of the qflow. Okay, so right now what I'll do, I'll choose 180 nanometer technology, and here since I have mounted my terminal in desktop, it is showing Verilog module name as desktop. Okay, so but you can also mount this terminal in any place also, and you can source your Verilog file here. So I am sourcing the same S44 what we have seen it in today morning session. So I'm sourcing it LUT S44. Okay, so once you have done that, you have to give the module name of S44. So I will open this. Let me tell you what is the name of that module name. It is LUT_S44. So we will copy it and we'll paste it here. Okay, so that it is been done. Okay, now we have to run this. So first we are checking the sanity. So sanity check can be done only in this. You can see how the sanity check has been done. What is mean by sanity check? You can check whether whether the Verilog program is having all the it is not having any bugs. Means you can see whether the program is complete. It's not having any syntax errors. That you can check, and it will check the timing libraries which is required for the whether you have pointed out the timing library, whether you have told to the compiler that whether you have you are going to link this timing library for getting the netlist or not. Okay, so that it will check here. That is nothing but your preparation phase. So first we are running this preparation phase. Yes, you can see it has been done. Once it is done, you can see it is telling okay. Okay, so if there is any error, okay, if there are any errors in this means, then it means that your program is having some issues. So you need to check the program. Maybe you need to have an offline compiler like iVerilog or something. You need to see find where is the syntax error is there. You need to correct it, and then you have to load it back here. Okay, so now this is done. Now we can go for the next stage, that is synthesis. So just like Viasis, here also we are morning we have Viasis. You can see that in our presentation. I have a OpenLane has Viasis. So here this synthesis means it is converting your Verilog program to a required technology specific netlist. So you are using Viasis only here also. So I will click run here. You can see this is having some issue. Okay, so it is failing here. So this I have loaded this to tell you that it is having some issue. So which means that this may not be having the when you are converting this design to some other format. Okay, you should ensure that the same that particular program is having, see, for running the particular program, whether the standard cells are present in the library or not. Okay, in your technology library, whether it has the timing library, whether it has the required technology files or not. Okay, so if not, it will fail here. So what we will do, we'll load some other program. Okay, maybe I have another program. I will load it that. Okay, settings. I will load another program, that is FSM. Okay, so now I will, the name is, it is named as my FSM. So I'm running here. So you can see preparation is done. Now it is loading Oasis. So you can see it is loading the complete design. So it is performing each and every step by itself. Okay, once it is done, okay, you can see what are all the things it has been done, what are all the cells it has performed. I will start from the beginning. You can see first it is converting your my FSM into a Verilog netlist. Maybe you can see that what are all the synthesis, while synthesis, what are all the standard cells it is being used, okay, in each and every phases. So you can see this. Okay, if you click this, you can see what are all the things it has encountered. Okay, what is the standard cells it has been used, it is actually using. Okay, you can see how many standard cells, how many AOI inverter, how many NOR gates, how many 3 input NOR gates with the drive strength. So all the stuff you can see over here. Okay, right, this is about our inception interpretation in our synthesis phase. Next is in placement. So for placement, Qflow is using a gray wolf algorithm. Okay, for placement, I hope it is, we have studied, I think the students might have studied in ASIC design, or if they are studying physical design automation, they might have used, they may studied there. So they are passing the macro and they are performing gray wolf algorithm, and it encounters totally 9 cells are required. Okay, the total cell width and total area and height of this also you can see it over here. Okay, so yes, it is performing gray wolf. Okay, it is inserting the standard cells. It's a min cut placement. Gray wolf algorithm is a min cut placement. So what it does, it first find out what is the area, then it divides the area in such a way that it can accommodate each cell in a given in one of the area. Okay, in one of the partition space. Okay, so it performs that, then it performs routing also. Okay, so after this, in static timing analysis, you can see what are all the paths. Okay, how many paths are there? Totally 2 paths it encountered. So in that path, you can see what is the default frequency it has been computed, and you can also see what are all the timing in those paths. Okay, what are all the timing is available in those paths. Okay, so next, when the design is routed, you can see what is the again what happens to the how many stages of routing. Again, it is also performs uh, uh, iterative routing. Okay, to iteratively optimize the various parameters like wire length and timing. So once it get optimized, it again checks the post route STA. So here you can see what is the delay in the different paths. So you can compare what is the means before STA, what is the delay, after STA, what is the delay. So you can compare these two things. There might be some small difference. You may encounter that. Okay, so after that, you can see what is migration. Maybe the migration report you can see here. Then DRC check, you can see whether you have any DRC or not. You can see here there is no DRC. Next thing is that you can see about LVS. So yes, LVS means, I hope all of you know, it is layout versus schematic. What are all the things it has been used in layout, and what is the schematic check it has been done. It will check whether the same things are available in the layout as well as in the schematic. So yes, you can see that the circuits match uniquely. And then you can see the GDS also. Okay, you can see the GDS is also generated. So the layout you can see here by just clicking edit layout. Once you click edit layout, for layout, for viewing the layout, this Qflow is using Magic. Okay, it is using Magic layout editor. So you can select this to see the layout. So this is the layout of the FSM what we have synthesized. Okay, hope is it visible to all of you? Is it visible? Whether the layout is visible? Okay, so this is how we generate layout in this using this. Thank you. Using this Qflow. Okay, so you can also perform different experiments in this. What you can do is that you can partition the design. Say, for example, I have given a netlist. What you can do is you can apply some partitioning algorithms like KL algorithm and FM algorithm, and you can partition the design. So when you partition the design, what happens? It may have different logic cells. So each you may be loading a different module. Your partitions will have different number of standard cells, right? So based on the density of standard cells, what happen? The routing may change when you go for a placement. Okay, the modules will be located in different position. So what happens? Based on the synthesis, there may be change in the positions of the modules in the layout. So when you do that static timing analysis, you can observe that what is the change in the static timing of the particular partition. Okay, so yes, you can find that there might be some small changes in the design. Okay, so this is how we have to use Qflow. So any doubt in this? If you have any doubt, you can ask me. Any doubts, participants? So I have done the, I think you might have in this workshop, you might have studied about the microwatt. Okay, I have done the layout of that. So I will show you how it is.
Srinath sir, sir, one
Yes.
question was there from the participant. I don't know whether it has been addressed or not. So the question is, the
Okay.
synthesis is fail in initial stage only. It was asked by Mr.
Yes.
Ravi Kumar Reddy.
Yes. Yes. Yeah. See, the synthesis. Yes. If your program is wrong, it will fail in the initial stage. And if while doing synthesis, see, if your program is wrong, it will fail in the preparation stage itself. That we call it as a sanity check. Okay, but if it is not mapped with the technology library, what you are pointing out here, we have pointed out 180 nanometer. If it does not have the required standard cells for synthesis, so the synthesis will fail. Okay, if the library does not have the required standard cells for performing synthesis, the synthesis phase will fail. Okay.
Yeah.
Any other doubts?
No, sir. No, sir. Thank you. Thank you, sir.
Okay, so then I will show you the layout of the open lane.
Huh? Adoro. Adoro.
So I stored it in SPM. Just a minute. Okay. Okay. So I'll share you the floor plan of the microwatt. Okay, so to generate the floor plan, what we have did is actually the microwatt is written in VSDL. We have converted into Verilog. So to convert that, we have used an open source converter called as a GHDL. Okay, we converted the VSDL into Verilog because OpenLane does not allow direct compilation of direct running of VSDL programs. Okay, so it accepts only Verilog program. So we converted that. So after converting it, we got a Verilog RTL of microwatt. Okay, so but still, nobody cannot replace the original peoples. Okay, so this Verilog is still having some issues. Though it passed synthesis and other things, certain macros it is failing to convert it into a exact failing to convert for generation of layout. But however, it has passed this floor planning stage. Maybe I will show you how the floor plan looks like. Okay, so I will use KN layout again. So KL layout. So it has OpenLane gave us microwatt underscore wrapper dot floorplan dot def. So I will load that. Okay, so this will load my floor plan. So a few minutes. So you can see to load the floor plan, how many lines it is loading. It is almost more than, lot of lines, okay, in kilo. So this is the actual layout in floor plan stage. Okay, this is the actual layout in floor plan stage. You can see in this layout, yes, the layout has some cells, but it's not complete. Okay, it's not complete uh, because as I told you, right, it has some issues in during the other stages of the physical design process, that is your um, uh, placement and routing. Okay, but in floor plan stage it has passed. So uh, just to show you, I'm just sharing the screen. What is the floor plan we got? Okay, okay then. So thank you. So I thank everybody. If participants, if you have any doubts, you can ask. Any doubts from participants? Participants, okay. So I'll give some exercise. You can solve that. You can change the in your open line for the existing design itself. You can study what happens to the if you're changing the clock period, how your design is working. Maybe it will be used for the new learners who want to learn, really want to learn what is physical design, what is the impact of clock in physical design. Okay, in an IC, how it um, changes your static timing parameters, how it impacts on it, static timing parameters, and how, see, changing the size of the power grid network, how it will have an impact. We may think that, okay, power pin, we may think the pins, IO pins are placed, at a default position, right? When I'm running the open lane, you might have seen IO pins are placed at the default position. But you can also change the positions of IO pin, and you can see how the parameters are changing, like IR drop, how it is changing. Okay, even static timing analysis, how it is changing, how it is affecting congestion, how it changes, what is the impact on congestion and wire length, all these things. And even power dissipation also has an impact. Okay, so I request all the participants to to study all these things. Definitely it will be useful for you to know if you are really want to kickstart your career in physical design. Okay, so any questions from participants? Any questions? Okay. So then, ma'am, I will leave the session to you, ma'am.
Sir?
Yeah. Anything else, ma'am? There is a question in the chat box. Which book is the best for learning and teaching? Okay. So as of now, there is no books, available. Maybe you can go with. I would recommend Sherwani. That is the best one. Naveed Sherwani, Physical Design Automation, for to know some concepts of physical design. That is the best. For learning this open flow, open lane and Q flow, there is no specific book. Yes, we need to rely on uh, internet resources, and there are other videos. So videos are there for how to install, but how to have a new program, how to have a new program, how to interpret from that what is happening in the open lane. I think there are no videos. So I think this is our first video. This is the very first video which will be there in YouTube, I think so. How to interpret, how you can load a new program, and how things are happening inside the open lane. What are the limitations of the open lane? How to install that? Even Docker installation. I think there are no videos. Okay, for Docker with open lane, there are no videos. Okay. So yeah, yes, I can send you the link. People from eFabless people, they have given a lot of videos on this. Maybe I can share it. I'll share it very soon. Any other questions?
Srinath,
Yes.
give me a
I'll share
minute.
the link. Yes.
Give me a minute, Srinath.
Yes.
So participants are requested to wait for a few minutes. So Srinath sir will share with you the links for those videos, and then we'll be starting our next session. So please stay connected and wait for a few minutes.
So yes, I have given the YouTube link, okay, for installations, okay,
Okay.
in your Windows operating system, okay. But Windows operating system, again, you need to have some software like VMware to install. Okay.
Yeah, thank you, sir. And participants, if you have any queries for Srinath sir, you're free to ask in the chat window. Srinath sir, I guess there are no more questions from the participants end. So
Yes, ma'am. Yes. So I think I thank the committee, the Open Power Committee, and the EICT Academy, from IIT Guwahati, for giving me an opportunity to present, to present. And I thank Mr. Ganeshan Narayan Swami of IBM for giving me an opportunity to present my skills. And I thank the entire community and the college, my SRM Institute of Science and Technology, Department of Electronics and Communication, for allowing me to present here. Thank you all.
thank you. Thank you, Dr. Srinath sir, for the wonderful and informative session. And we are pretty much sure that the participants have really enjoyed the session. Thank you, sir, for giving your time. Thank you.
Thank you, ma'am. Thank you very much.
Yeah, thank you, sir. And participants, now we'll have a short break of 10 minutes. And then again, we'll start the session by 12:55. So we'll start our next session by 12:55. Thank you. So please stay connected. Do not get disconnected.
Ma'am, can we start the session?
Sure, Abhinandan sir. So participants, welcome back again. We'll start the third session now. The third session will be of Mr. Jean Paul Chaput, sir. So as we already informed that because of the time constraint, so two of our speakers will not be able to like deliver directly on the platform. So the second speaker is Mr. Jean Paul Chaput, sir. So we have with us Dr. Abhinandan, sir, who will be coordinating with us to play the recorded session of Mr. Jean Paul Chaput, which he recorded for this particular program. So I'll just give a brief introduction of Mr. Jean Paul Chaput, sir. So he holds a master degree in microelectronics and software engineering. He joined the LIP6 laboratory within SU, formerly UPMC, in 2000. Currently, he is a research engineer. Currently, he's a research engineer in the analog and mixed signal team at LIP6. His main focus is on physical level design software. He is a key contributor in developing and maintaining the Alliance Coleus VLSI CAD projects for CMOS technologies. In particular, he contributed in developing the routers of both Alliance Coleus and the whole Coriolis toolchain infrastructure. He is now a key contributor in extending Alliance to the analog mixed signal integration for nanometric CMOS technologies. So with this short introduction of Mr. Jean Paul Chaput, sir, I would request Dr. Abhinandan, sir, to kindly coordinate and play the session of Mr. Jean Paul Chaput, sir.
Yeah, thank you, ma'am. So let me start that video. And as usual, if you have any questions, please send it to us or write it on chat on the chat box. I would actually collate it and then send it to Jean Paul and then get back to you. Okay. So
everybody and welcome. Hello everybody and welcome. You're about to see a tutorial about the Coriolis design flow, which is aimed at making ASIC. In order to correctly use the design flow and parameterize Coriolis, you will first need an introduction about the steps involved in making an ASIC. So the presentation will be organized as follows. First, I will make a short introduction about what is it to make an ASIC. Then present the two main steps of the making an ASIC, which are the placement and the routing. Then I will go to the full design flow and present the reference of the free tools I use. And finally, I will end up with the demonstration itself. So, what is making an ASIC about? Basically, an ASIC is just a drawing. This is this drawing that you send to the foundry. The foundry being the ASIC factory. But it is not just any drawing. It is a very complex one that must follow lots of complicated rules. We call them design rules, so that the factory can really fabricate it. In our terminology, this drawing is called a layout. Now, this is the most basic diagram for the design flow. It is a V-cycle, meaning that the left-hand side of the diagram breaks things down into elements of the standard cell library, and the right-hand side did reassemble them in a complete layout. The entry point of the flow is a RTL description, register transfer logic, which you should be already familiar with, at least I hope most of you, because it's what you feed to an FPGA compiler. So it's the same description, exactly the same. But we apply it a different treatment. What we do is logical synthesis on the left hand, which breaks the logical equation into logic gates, which are 1-bit elements, like, for example, the NAND2 gate, which is represented in the blue background, and which have a layout equivalent. The basic idea is to break things down into elements that have a layout equivalent. Once we have done this step of breaking things down, we reassemble the whole thing under the shape of a layout using the place and route steps. And what you get in the end is either a symbolic layout, this is the AP file, or a real layout, this is a GDS2 file. We will see in the next slide what is the difference between a symbolic file and a real layout. As I just said before, Coriolis support two kinds of layout, the symbolic layout and the real or physical one. I will start by a brief history of the symbolic layout. The symbolic layout was invented in the 1980s by Mead and Conway based on the observation that whenever you change of foundry or technology, what you mostly do is a shrink. So instead of drawing one standard cell library per technological node or foundry, they decided to create an anonymous unit, which is called the lambda, and to draw their standard cell once and for all with that unit. Then, when they wanted to target a given node, they just have to make a shrink, like it is shown in the right part of the slide. It is slightly more complex than a shrink because you also add a small delta on the wire width and a small delta on the extension of the segment. But it is mostly a shrink. This technique is very successful, but it has the drawback that you cannot achieve the same density than with a real layout. It is at the start of the Moses service in the US. One other advantage that was enforcing at the time is its independence toward NDA. One of the limitations when you work in a real layout is that you have to sign an NDA, which prevents you to share your design, to share the layout of your design, which can be problematic in terms of security when a third party wants to see or check that the layout is really what it is meant to be, or some kind of audit or other thing. And it's come increasingly as a concern. So Coriolis can support both. So now I will talk about the goals of Coriolis. The first goal is to provide a platform which is suited to academics to allow them to make algorithmic on any experiment which may need to modify the database or any internal components, which is something you cannot achieve with commercial software because you cannot tailor it to your exact needs, and you may be prevented to publish your results due to NDA agreements. And lastly, you may have backward compatibility problems. It has already happened that an academic base his work on a certain version of a tool, and then the next version breaks things. So it's quite painful. The second point is to build a free and open source community. By freeing the layout and freeing the code, we hope that people can start to share their layout and create a community. Third, we want to open the markets, the ASIC markets, to the SMEs, because there has been a drop in price of the mature technologies. Now, making a chip in an old technology is affordable for a small company or small enterprise. But the cost of the software tools or the EDA tools are still very high. The license fees are very high, so it prevents them to use it. So by providing something free, we hope to help them. Another trend that has arisen recently is the question about security. You want to ensure that your chip has not been modified to include some kind of Trojan or other malware. You want to be able to check that your chip is actually what it was meant to be. So having free tools for that is a plus. And lastly, we may have some problem with long-term maintenance. For example, nuclear power plants want to have the same component for a lifespan of 50 years. So imagine a chip or any design that lasts 50 years, and it's quite complicated. By making everything open, we hope that people can ensure the continuity of their design. So now we will narrow the focus of this presentation, the use of Coriolis as a silicon compiler. But to understand the error that can occur, you must be able to orient yourself in the design flow and to understand what is possible and what is not. To illustrate that, I will present a representative example of a small design. The complete design flow is made of a collection of various tools. This collection may seem a little bit complex at first glance, but it is the result of history. At first, there was the Alliance toolchain, which was complete with logical synthesis, physical synthesis, verification tool, and timing analysis. But it was limited to symbolic layout and can only manage up to 10,000 kilogates. So by the start of the year 2000, we developed the new Coriolis part, which is a re-implementation, but only of the physical synthesis. And this one can handle at least up to 500,000 kilogates, assuming that it is the upper limit because I didn't get my hands on bigger designs. So the toolchain is an assembly of various parts, which are first the tools coming from Alliance, because we didn't suppress all the tools. Some of the tools, especially in the verification and the translation between netlist format, for example, between VHDL and Verilog, are still used. Then there is, of course, the Coriolis physical design steps, but also IOSIS, which you should know for the logical synthesis, because it's the same tool that you use for FPGAs. And finally, the Alliance Check toolkit, which provide a set of scripts to automate the making of ASICs and a set of examples. This is on those sets that we will work later. So the 3 parts came from Lipsys, and of course, IOSIS is not hosted by Lipsys. Now, let's have a look at the placement. On the left side of the slide, you see the netlist expressed as a schematic. That if you see the signal like A and B, connecting gates expressed as logical Boolean function. On the right side, you see the equivalent in terms of layout. Each gate is replaced by its equivalent layout. And what we want to do is place all the layout of the gates inside the designated area without any overlap. And with respect to some optimization criterion, like the total wire length of the design, that is the total sum of the wire length of each net. But there are also other criteria. In this presentation, I will not talk about the algorithm involved in the process. I only talk about the problem to solve so you understand which are the parameters at play. As I said, the placement of the standard cells must be done without any overlap. But it goes beyond that. As you can see, the cells are organized in rows, which are also called slices. The consequence is that each standard cell must have the same height as the other. It has also a pitched width, that is a width which is a multiple of 5 lambda here. You can also notice that the power lines are shared, which means that every 1 row over 2 must be flipped vertically. This is the sense of the arrow you see there, here in normal orientation and here in flipped orientation. There are also blank space that remains because of the algorithm, which needs at least some free space, and for other reasons that we need to sometimes insert extra components like polarization contact to avoid the latch-up effect or diodes to avoid antenna effects. After having looked at the standard cells, now let's look at the metal layer. Metal layer will be used to build the wires that will connect the standard cells. The metal layers are stacked on top of each other and numbered from the substrate, meaning that metal 1 is the closest to the substrate and metal 5 the farthest. There are also cuts between the metal layer. The first one is called a contact, meaning that a contact is a cut between the substrate in green and the first metal layer, the metal 1. Other cuts like this one, and this one, and this one, are in fact vias. A via connect 2 metal layers. The metal layers are then organized in preferential routing directions that you can see on the right side. The metal 1, for example, is in the vertical direction. Then the metal 2 in its perpendicular, that is horizontal. Then metal 3 vertical again, and metal 4 horizontal again. So this is crisscrossing the design. This is called Manhattan routing for those who may not know already. The routing tracks are regularly spaced. The router must be able to put a via at any point in the track without generating any DRC violation. To ensure that, we compute the minimal distance of two tracks for which this condition is always verified. For example, here, the minimum side of a via is 3 lambda. Then the minimum distance of metal 2 side by side is 2 lambda. This yields to a 5 lambda pitch. The pitch is the distance axis to axis between two neighboring tracks, and it will ensure that the routing is DRC clean by construction. Now we put the two of them together. That is the standard cell layout at the bottom and overlaid the routing tracks. This is called over-the-cell routing, in which the routing area is overlaid upon the standard cell area. This also means that the number of wires that you can pass over a certain area is limited. So this is also another reason why you may have to expand your placement area. It is because there is not enough space to make the routing. And that is highly dependent on the kind of design we are making. Some design do not require a lot of wire and can be placed without a low spacing factor, but others may need a bigger one. Now, if we try to solve the routing problem head-on, it will not work because the sheer amount of data is too big. So we must abstract even more our problem. We do so by introducing the concept of G-cell. A G-cell, as shown here on the bottom left of the figure, is an area of, for example, 10 by 10 tracks, which is abstracted into one point. Then we rebuild a routing grid, which is made of G-cell considered as one point and edges that represent the sides here. So, and at that point, this explains the two steps of the routing. First, the global routing on the generic grid, on the G-cell grid, then the detailed routing, which finishes it at the level of the routing. Here is represented the global routing grid in green, with the node, each node is a G-cell here, and the edge connecting them with their capacity. As I said, the capacity of an edge is the number of tracks that you can pass through that edge. For example, here it's 10. But it is too abstracted a model because it assumes that if you can pass 10 tracks on the edge, you can also pass them all around the G-cell, which is not true. The G-cells contain standard cells that you have to connect to their connectors, and inside you can also have dog legs, turns, and whatever is needed to achieve the detailed routing. So the G cells are not as transparent as the edge seems to indicate. So to modelize that congestion, the internal congestion of a G cell, we artificially decrease the capacity of the edges. This explains the two Coriolis parameters, which are Ketana.htrect reserved local or vtrect reserved local. It's quantities that we subtract from the edge. So obviously, it will make the work of the global routing more difficult, but is the one of the detailed router. So it's a trade-off. And it's a trade-off that you may have to change for each design. Maybe in the future, I can make the router better so it can more smartly guess itself that number. But for now, you have to do it yourself. After presenting you the basic step of place and route, let's have a look at the design flow as a whole. And we will start with the symbolic version of the design flow. In the next figure, I will try to respect a color code, which are blue for components that comes from Coriolis, green for the one that comes from Alliance, and red for the one that are third party, not done at Lipsix. And lastly, what is under a light red background is covered by NDA, which means the part that you cannot share with anyone. So the symbolic flow starts with an RTL description, register transfer logic, which can be written in VHDL, Verilog, or RTL-IL. It comes itself from an HDL language, meaning hardware description language. There are two kinds of hardware description language, like MNITJ, which is Python-based and may be more suited for people with an electronic background, while Chisel or Spinal HDL may be more suited for people with computer science background. The first step of the toolchain is to perform the logical synthesis, which break the RTL description into a gate-level netlist, which is also expressed in Verilog or VHDL. At this point, you can also perform a validation with GHDL or other tool. In fact, you perform a resimulation. That if you have simulation pattern that you did apply on your RTL description, and then you can reapply them all the same to the netlist to see that, check that the logical synthesis did really make the same design. It is not perfect because you need a complete coverage, which is impossible to achieve, but yet it is a good verification. Then we have the steps we just discussed, that is the place and route with the physical synthesis, which will give you a symbolic layout that you can validate. This will be detailed in further slides. And after that, you can still share the symbolic layout. But to send it to the Foundry, you need to transform it into a real layout by targeting one technological node, which is done with the S2R tool, which contains translation rule, which basically make the scaling, and then you get the GDS. That GDS can also be checked with K-layout or any commercial tool. The real design flow is somewhat shorter. It starts the same as the symbolic flow, but the logical synthesis and the physical synthesis must use a cell library which is proprietary, or at least non-publishable. Same goes for the generated layout, which is GDS, and which is covered by the NDA, so cannot be published. And as there is no real world, at least real layer verification tool, we cannot verify it with free tools. But you still have the possibility to check them with commercial tools, of course. In the last year, we have seen an interesting trend in the sense that Foundry started to release some design kits without NDA, like the Skywater 130 nanometer, which is a very interesting development and, that we keep a close eye on. Now, let's focus on the logical synthesis stage. It is needed because it makes use of a lot of files of different formats, and you will see them when you run the design flow. So you must understand what they are and where they come from. So I have already spoken of the VHDL and Verilog file, but you may also see RTL, EL, or BLIF file. BLIF file is in fact the real output of IOSIS. IOSIS doesn't directly generate VST file. It generates BLIF file, which is a kind of netlist file, but an older format. This format we have to translate using the BLIF to VST program. VST itself is a kind of restricted VHDL format for netlist only. It is a format which is particular to Alliance, but compatible with VHDL, basically. All that transformation process is taken care of through the makefiles. That is, we have rules that automatically perform the various translation. But still, you will see the resulting file, so you may understand why they are here. Now, the physical part of the flow. The place and route is not done through makefile rules, but through a single Python script. This is the script you will have to modify to achieve your place and route and to achieve a correct design. So what does this script do? It starts with the input netlist, which is in VST format, the one we just saw about. So this is design.vst, meaning that design is the design you want to realize. So what does that script do? First, it builds a fixed floor plan. That is from the design, which is only the core of your ASIC, it will build a complete chip along with with I/O pads. Then it will perform high-fan-out net synthesis if required, or if enabled. Then build the clock tree trunk, meaning the H tree. Then place the standard cell around the clock tree trunk. Finally, achieve the clock tree by connecting the individual DFF to the leaves of the clock tree, then perform the global route, perform diode insertion if required, and finally perform the detailed routing. The output is design CTS-R because the netlist is changed. By inserting the clock tree, which is mean here CTS, we tell that the netlist has been changed. So we don't want to override the initial one. Then we have the netlist at the chip level and the API file if we are running in symbolic mode, or directly the GTS file if we are running in real mode. You may also notice that the two design script make in fact a lot of things which are done either in C++ or Python. This is highly integrated, and you will only see the Python interface, but below that, you have a mix of Python and C++ scripts. Of course, you will get a template for this file, because for each design, you only need to modify a few lines. As we automatically create the top-level hierarchy of the chip from the core, this hierarchy is fixed. So here is a small schematic of the hierarchy. First, the legend. The enclosing box is the cell, which is the model. And inside that model, you have instances that themselves refer to other cells. This is the way we describe the hierarchy in this schematic. So on the left-hand side, you have the layout, and on the right-hand side, you have the associated hierarchy. So we start by what you supply, which is the core. The black part is the core, and this is the netlist that you did supply. Around that core, we wrap the core inside a corona intermediate layer, a level of hierarchy, which is as one instance, which is called core always. And this level is also called corona. It's an intermediate level inside in the layout between the I/O paths and the core. It is some kind of adapter. There are technical reasons to do like that, but I won't explain it there because it's too complex for this lesson. So, wrapped around the corona, we have the final chip level, which contains all the I/O paths here, I/O1, I/O2, and so on. Those are the paths which are around the chip, and the corona, which is at the center. So you will see all those netlists appear in your directory. So don't be alarmed, it is perfectly normal. Finally, let's talk a little about the validation step. What are the main validation when making an ASIC? The first one, starting from the layout here, is to perform a design rule checking. The design rule checking will verify that all the rules for drawing your layout are verified. So the fabrication will go well. It means that it is not, the design is valid and will return something which can be fabricated. The second verification is to check that the layout is indeed the design that you wanted to do. To do so, we need an extractor which will read the layout and rebuild the netlist from the layout. And then we can compare the original netlist at the specification with the extracted one coming from the layout through an LVS, layout versus schematic, or in our case, layout versus extracted, to see that we really have the design we want. Those are the two first basic steps. And then we have also the timing analysis. Not only do we want to check that the netlist matches, but also that there is no timing problem inside the design. We perform a second extraction here, which gives us a netlist but with timings, and then we run through a static timing analyzer. And we can see if there are old violation, long chain, and so on. Unfortunately, to perform those steps, we still need many information that are kept in their NDA. So maybe you will not be able to perform that step correctly. Here are the references of the main tools I did build the design flow upon. It is not complete, but it is the most important ones. So we have, of course, IOSIS, Alliance, Coriolis, the Alliance Check Toolkit, K-Layout, and FlexLib. FlexLib is a library to perform designs. We will see that after. And finally, the most fun part, having a demo. We will go through the basic step to build an ASIC with the Coriolis design flow, starting by setting up the working directory, customizing the script and makefile, running it, and seeing how to tune your ASIC to get the best result or to make it work. And finally, some nice feature on how to see what you are doing. After introducing you the basic of making an ASIC, it is time to start the demonstration. I assume in this demonstration that all the tools are already installed in your system. That is IOSIS, Alliance, Coriolis, and Alliance Check Toolkit. The example I will show is already present inside Alliance Check Toolkit. So first, let's create a directory into which we will work. We change into it. We need to create a symbolic link to the MK directory of Alliance Check Toolkit into this directory. This link will hold the default rule for the makefile. So here we are. The link is ready. Then we copy the file from the example directory. Same as before. We copy from the CMOS45 variant of the example, which is a symbolic technology. So we copy the top level makefile. We can then copy the configuration file for Coriolis. This is a directory, so we make a recursive copy. Then the RTL description of the design we want to use. In this case, it's in Verilog. And finally, the do design script. Here we are. We have all the relevant files needed to run our example. But before we do that, we can have a look at the various files for the example. The configuration file of Coriolis are put inside the Coriolis2 directory. Let's see what it contains. It contains the classical init.py file, which tells Python that the Coriolis directory itself is a module and it can be imported. Then we have the setting.py file. Here, the most important line in this file is this one. This line, this import, tells Coriolis to use the CMOS 45 symbolic technology. CMOS 45 symbolic technology is a symbolic technology aimed to be used with FreePDK 45, hence the name. Then we have this line, which tells Coriolis which signals should be matched as clock, or should recognized as clock. It is a regular expression pattern. So every signal matching those patterns will be understood as clock. The two last lines set up the library, the cell libraries. The first one is the standard cell library, holding the classical cells, meaning NAND, NOR, XOR, and so on. The second one, NIOLib, is the library dedicated to the I/O pads, which can be less portable than the others. So these are the two libraries. Next, we can have a look at the makefile itself. The makefile contains all the information to run the scripts. So at first, we say that we want to use the IOSIS logical synthesis step. Then that for physical synthesis, we want to use Coriolis. For technology, we want to use CMOS 45. This is a duplicate from the technology of setting.py, and it should be the same. Otherwise, you will run into trouble. We don't want to work in debug mode, of course. Then we have the netlist part. This list is just the list of VST files that may be generated. The first one must be the core. It must match the Verilog file. It is the same without the extension. And it must be the first because it is the core by convention. Then we include all the rules from the MK directory. Here you see ./MK. So all the rules are supplied. Not all the rules, unfortunately. The two following rules must be included directly in the file, and eventually they will make their way inside the designflow.mk. But for now, they are not there. And they govern the running of toDesign. It's to trigger it's the rules that manage to run toDesign. And finally here, there is a bunch of shortcuts for the rules that allows to run each stage separately. BLIF will just run IOSIS, because BLIF file is the output of IOSIS. VST is also the output of IOSIS, but translated into the Alliance VHDL format, the .vst. Then we have layout, which triggers the place and route stage. And finally, LVX, which triggers the layout versus extracted verification. Druck doesn't work yet. We need to configure Druck to work properly with this technology. So don't try to execute Druck. It will work, but give you errors. So here are the main file. And finally, let's have a look at toDesign. We will come back to it later. But the one more important line is this one for a standalone run. You can run toDesign standalone directly from the command line. And in this case, this line triggers the loading of the setting.py file. So Coriolis environment would be set up, but that would not be enough. You will need to set up also some environment variable which is tedious and prone to error. So this is why there is a makefile which takes care of all the initialization of all the environment variables. But if you want and if you know what you are doing, you can do it standalone. The script contain, the Python script must contain at least one function, which is script main, and this function will be executed by Coriolis. Coriolis will specifically look for that function. If it's missing, it will do nothing, maybe complain. And finally, if you want to execute standalone, you need also to add this small piece of code with just execute script main when the script is run standalone. This is classic Python strategy. We are now ready to proceed to the logical synthesis step. This is quite simple. Just type make VST. Then Yosis run and the glyph to VST script. We now have the VST file. The VST file is the netlist format, which is VHDL based and which is accepted by Alliance and Coriolis. As we may want to run the place and route stage multiple times, we can back up those VST files. So here we go. And copy the VST file and the glyph file into ref_VST. This way, we can run the place and route multiple times with deterministic results, meaning that we are sure to start from the exact same state. The next step is the place and route, or physical synthesis. It is also quite easy, just type make layout. For a first trial, we use the text mode. It is slightly faster and much lighter in memory. We see here the placer doing its job. In this small example, it is quite fast. Then the global router here, and finally the detailed routing. Here we are finished and our layout is ready. We can see it if we check in the directory. The epi file has appeared. Epi file for Alliance Physical is the layout format for symbolic layout. So we have our symbolic layout. The last step is to perform some checking. For now, we can only perform LVX. So quite easy also, make LVX. And you see that, of course, its netlist are identical. Make LVX perform two operations, which is the first one, the extractor, known as Cougar, reads the layout and regenerates a netlist in a slightly different format, which is IAL, Alliance Layout. No, sorry, Alliance Logical. And then it's compared with the VST file, which is the original one. And we see that terminals are okay, instances are okay, and connections are okay. So the two netlists are identical. We can see the resulting layout with make CGT. Here. You can use the library manager here with Control M and look at what's present. The end result is chip_R. So we want to load the VST and the AP, the logical view and the physical view both. They will be combined inside Coriolis and load. Here we are. We have our layout. So That's the first way, that's the automated way of getting the layout. After running in text mode, we can also run in graphical mode for debugging purpose or pedagogical purpose. But first, we need to reset the design. This is done by doing make clean. The design has been reset. To avoid to rerun IOSIS, we can just copy back the file in ref_VST. But first, I will also enable the breakpoints inside DoDesign to perform a step-by-step run. So I look at DoDesign and I uncomment the breakpoint level. This will make the script stop at some desired points. So we run MNITJ, which start a blank viewer, and then we can load the Python script. Here, DoDesign. Do not put the extension, just DoDesign. So you see, we reach the first breakpoint, which is right after the creation of the chip and the corona level, and also the basics of the clock tree. What you see here is the buffers that will be used to create the clock tree. So now here we are. Now the trunk of the clock tree has been created. You see the wires. There are two clock trees, one for the clock and the other for the reset signal. This explains why the lines are doubled. This is not because drawing too much. All the wires are duplicated. So now we can run the placer. What you see here is the placer at work based on the simple algorithm. And this is the second placement that you see. The one which is uneven and which at the end came even. So you see it slowly smooths things until it reaches a less than 10% difference. Here you see the end result of the placement, but without the filler cells put in. This is why you see a lot of free space. Lot, not so much, but you see free space. Then the free space is filled and the power lines are drawn. Now we are ready for global, then detailed routing. In order to follow better the process, I will outline one net. So I will use the inspector.
Hello, Abhinandan sir.
Then
Yeah.
I call do design.
Can you hear me now? Can you hear the video, ma'am?
Yes, yes, yes.
Pop up an error. And the error is the core is too wide to fit into the corona. So this is the kind of error you get if your core is too big. So you can solve it by either shrinking the core, if it's possible, or expanding the whole chip size. Now, secondly, we make another kind of error. I restore the right size for the core, but I will slightly shrink the chip itself in horizontal direction. I remove 100 lambda on the width of the chip. What happens now? This time, we get another error telling us that the chip is not wide enough to put all the pads on the north side. If you get back to the previous presentation, to the previous part of the presentation, you will see that the north pads are side by side. So removing any length from the width of the chip causes an error. So this is the other kind of error. We will now look at the router's parameters. So if I also change do design to change the number of reserved tracks for the local routing and put them all to 0, for example, and restart my script, what will happen? So the placement runs. I did restore the right parameters. We have to wait just a little bit until it reaches the global routing. Okay, now you see that the global routing here, we'll wait just a little. First observation, here, the global routing didn't have to make any rip-up. Everything went fine at the first try. It means that it has a lot of space. And this is expected because I didn't put any local constraint on the G cell. I said that every G cell can go through as they want. They have all the capacity, they have the full capacity of all the edges. So obviously, this is much more easier for the global router. But on the other hand, what we see at the end of the routing is that we see the routing did not complete unrouted segments. That is, the routing has failed because it didn't have enough local capacities in the G cells. And you have a report here, and what you should look is there, that it says that you have 12 segments that are unrouted. The number here is the number of routed segments plus the number of unrouted segments. You have also the same computation, but for the total wire length, and also the statistics about how many horizontals were unrouted, 8, and how many verticals were unrouted, 4. So that explains why we need those parameters. So I will restore them to a much higher value, for example. Not the right one, but higher still. So I will put 3 here and 3 here. We'll start to reserve tracks. And here we go again. So we wait for the placer to work. Okay. Maybe I should have chosen something faster. Okay, not enough. See that we got the same error as before. So we must increase. This may be your work to increase the parameters until it works, but not too much. Because otherwise, if you increase them too much, you will make the global routing too difficult. Here, if I go up to 10, I will make the global routing very difficult, but very easy for the detailed one. So, another try. In the future, I hope to enhance the router so it can guess better those parameters and ultimately guess them fully automatically. But for now, they are just manually set up. So here we go again. And now you see that the global router has a lot of problems. You see that this time, it took him 10 iterations and to not even succeed. At the end, it stopped at 9 iterations because there is a limit. I put a hard limit to 10 iterations. It can be changed, of course, but for now, for this example, it's at 10. So it didn't succeed. And it gives you an histogram of the saturated edge. And the funny thing is that even in that condition, it didn't finish the detailed routing. So the place and route is still quite sensitive settings. So you will have to try to adjust your parameters. So here we are. Thank you for attending this presentation. I hope it will be useful to you, and have a nice day.
Ma'am, ma'am, today I will upload this video also. Okay.
Okay,
I think
sir.
we are done with this session, ma'am.
Yeah,
So,
yeah. Yes,
okay,
sir.
ma'am.
Please continue.
Thank you. Yeah, thank you, participants, for the like we took additional 15 minutes to extra. Sorry for that, and I hope the session was good. Good. I will be sharing this video, also uploading it. So I'm almost done with that uploading, and I will share the link. And other thing is, please don't forget the Open Power Summit today. Okay. Thank you very much.
Yeah, thank you, Abhinandan sir, and participants. If you have any query, with regard to this particular presentation, you may post in a chat window, or you may also post in a Telegram group so that we can forward to Jean Paul sir. Thank you for your extra time. And thank you, Abhinandan sir, for the coordination.
Yeah,
And
thank you.
participants, the materials for day 7 and 8, so those are not uploaded, so will be uploaded.
Yeah, today you will get it.
Yeah, by
I'm in
today
process of
evening.
uploading. Yeah.
Yeah.
Okay.
Thank you all for your cooperation. Thank you.
Thank you.